For my talk, I'm going to speak about the use of phylogenetic methods for understanding human evolution. And for the purpose of the talk, at that part of my research, I really take humans as they are. That is just another ape. Don't feel offended, we are apes, we are all apes, special in many, many senses, but we are like that. That if we are to understand our evolution, the best approach is really to put humans on the apes family tree, which is exactly what I'm going to present with two different examples of applications of this sort. One regarding the evolution of our climatic tolerances, the other one regarding the evolution of our brain anatomy and functioning. Just a very rapid introduction, probably this is not even necessary. The genus Homo appeared in Africa some 2.8 million years ago. If a special mandible is recognized as human, but that's not important at the moment, with the handyman, Homo habilis, who happens to produce very simple, very ordinary stone tools, if the word ordinary applies at all to human stone tool technology. Later on, the upright ape, Homo erectus, was the first one to went out of Africa, as for the talk we were attending before. Sapiens means thinking. We are the thinking ape. We are special in a sense. So we truly are the thoughtful ape. We spend a lot of time thinking of others, thinking of ourselves. And this is a special quality of the human mind that probably is linked then to the production of what people understand as high cognitive performance, which is something special, which is exclusively related to humans, or at least we used to think it was exclusive to humans. Sapiens was of course, it was the ape to, the only one to survive, the one that came to dominate the world in a sense. We arrived in Europe around 54 kilo years ago, and Mandarin, according to the findings of Ludovic Slimak and his group. But there are other migrations outside Africa that apparently left no remnants there in the places where the fossils were found, such as at Mislia, Skul, and Kafze, which are the examples we have been shown before. The evolution, the technological production of Homo sapiens is marked by an event which most people understand as the Upper Paleolithic Revolution, which is the appearance, apparently sudden appearance, of a lot of art production, the production of ornaments, the production of cave paintings, and many other special behavior likely attached to humans and to humans only, or at least, allow me to repeat myself, at least we once thought they were just humans, which are apparently on no practical purposes. Even if now we are going to understand day after day as the research proceeds that they have, in a sense, a practical purpose, which is related to sexual selection. But I will get back on that later on. The revolution, as I was saying, is marked by the appearance of special lyrics, but also by practices which were unanticipated in the human fossil record, like the burials, highly ritualized burials of the dead, cave paintings, the production of statues. And this very piece, which is the one I like the most, the Lion Man on Höhlensteinstadel, it is so special because it is not something that could be directly observed in nature. You have to imagine it before producing it, because clearly it is the head of a lion upon the body of a man. So it's not clear, it's not just imitation of something which is around. They whoever the producer was, he had to imagine, or she had to imagine it in his head. But in fact, as it seems to be, the revolution is not just confined to Homo sapiens, because at least one other species was able to produce art, and probably used to bury his dead, that is Neanderthals. Most of these findings are highly contentious, especially this flute here. I forgot adding the name of the author. Is a Slovenian archaeologist named Sturk. Some of them, as I was saying, are strongly criticized. For some people, this is not a flute, but just a punctured piece of bone of a cave bear. Or maybe the stencils at La Pasiega was even the dating of these particular stencils and art, so to speak, are highly contentious. What they really represent, I don't know. To me, it looks like modern art, which means I don't understand anything about that. Or maybe those are easier to interpret, the talons at Krapina. These are eagle talons that were arranged to produce probably necklaces or something like that. And we know that Neanderthals were producing glue from the beech bark. The process is now understood easier than it was once fantasized. And even at Bruniquel, there is this very, very special arrangement of stalagmites in forming circles, which, by the way, means that you are not the first hominins interested into speleothems. The Singing Neanderthals, by the way, is the title of a very nice book of Stephen Miller. The point is that we are, year after year, discovering aspects of this, so to speak, cultural modernity that trace further back in time. For example, last year it was published on Nature, this finding by Barman and colleagues, coming from Kalambo Falls in Zambia. They are intentionally interlocked logs. And by intentionally, I mean that according to the authors, they were cut, the wood was cut just so that the logs could be interlocked, which reminds of kind of a construction, intentional construction. Or maybe a Gesher Beno, which is in Israel or Palestine. I don't want to offend anybody. No, I really don't know whether it is in Palestine or in Israel. They found evidence tracing back to 800 kiloyears ago of intentional cooking of grain in this case, the grain of this particular plant. And then you come to the famous track prints at Appisburg. They are nearly 900 kilos years old. What is special with that? They are footprints. Of course, this is special. It's the place where they are, which is far in the north. And of course, they were left by some other species other than Homo sapiens, of course. Which is special because at Appisburg, at that time, the climate was very, very cold, which means that they have to, some way, to fend off the problem of cold winters to live there. One of the problems is that, and this is where phylogeny matters, one of the problems is that it is very, very hard to find fossil evidence for many aspects, for many tools and products of this cultural modernity, basically because most of them do not fossilize. For example, the oldest basket tree we know about is, if I remember well, 9,000 years old, just 9,000 years old. So the point is that provided that we know what is cultural modernity, because cultural modernity, at least to me, is that kind of thing that if nobody asks you, you know what it is. The problem comes when you have to define it, of course. We don't know whether it is confined to Homo sapiens. We don't know whether the first Homo sapiens really is Homo sapiens. And we don't know which Homo species actually introduces the first aspects of cultural modernity. To the archaeological record, of course, it is very important to understand which species began producing cultural objects. From the cognitive point of view, of course, the most important thing is to understand when the brain of Homo started to work like ours. For a very long time in anthropology, the focus of this discourse really revolved around the idea of measuring brain size. Because we know we have a very large brain species in comparison to the body size, and Homo in general is a very species, genus or species have very large brains, and you can follow a trend through time, and this trend, which looks like linear, but in fact it is stepwise, because there is one species, that is Homo heidelbergensis, which really does a step in terms of increased brain size as compared to the linear trend, the ideal linear trend that goes up to Homo erectus. This has long been noted by the paleontological literature, so it's nothing new. The problem with brain size and with my neck and throat is that brain size doesn't tell the whole story. We have two very blatant evidence that this is true. One is Homo florescensis. His brain is 1/3 the size of modern humans, and yet he was able to produce, to live there on Flores, to live there in numbers for a very long time, and to left behind evidence of his passage there. Plus, it was able to produce advanced storing technology with a brain 1/3 of your size, which is a lot. Plus, there is now very strong evidence, and during the last 3 to 5 kilo years, the brain size of modern humans is shrinking. It's shrinking rapidly, with the end product being our politicians, of course. No, that's not just shrinking, it's malfunctioning, which is different. So let's see why phylogeny matters and how we can make use of it. For the first example, I just, together with my research group, assembled a human family tree, assembled a database of human occurrences through time, and then we decided to use to intersect the fossil occurrences along with the age uncertainty with the available paleoclimatic data in terms of basically precipitation and temperature and their variability through the year. And then we constructed what is called an habitat model, an habitat suitability model. I'm not going into the detail because I think that most of you know what it is. And then we study how fast the human niche, the human climatic niche was evolving, and whether this evolution was kind of linear according to what evolutionary biologists call the Brownian motion model of evolution, which is, the other name is the boring motion model of evolution, which is just the idea that new phenotypic values just accumulate over time in a linear fashion, or whether there are jumps, meaning that there are moments in time when the, in this case, the climatic niche evolution goes faster, immediately faster, or the converse. And we found one of these instances here. It's node 14 in this particular phylogeny, which is the node where Homo heidelbergensis, Homo sapiens, and Homo neanderthalensis belong. To do that, we apply a method, which was developed by my research group, by the way, which simply calculates the rate of evolution along the branches of the phylogeny. And you can also apply this method to account for phylogenetic uncertainty and dating uncertainty. And dating uncertainty is important because it brings about the uncertainty in climatic values being reconstructed. Then we get back in the original variable space. I can provide detail later on if you want, to calculate what is the extreme temperatures and precipitations that the species could subsist. And we found that for this particular group of, those are the species of node 14, that is Homo heidelbergensis, Homo neanderthalensis, and Homo sapiens, they can experience winter temperatures down to -20. I'm not saying they were happy out there at -20, of course. Quite the converse, I'm saying that they were endowed with tools, probably garments and coats, to fend off the offense of the cold. And in fact, this would explain why they were able to live as far in the north as at Naples, for example. Whereas for precipitation, we found no clear trend. So in a sense, you don't have the archaeological evidence, but you have the evolutionary evidence that those species, I mean, starting with Homo heidelbergensis, were able to defend themselves, their bodies, from the cold. And the only explanation that I can fathom for that is the production of coats. And if you go back into space, you immediately realize that the habitats, I mean, the geographic spaces that the species could have occupied are those non-blue, so to speak, areas over there. But what they in fact occupied, because of that acceleration, the evolutionary niche is much larger. How much larger? The size of a continent more, of an entire, it's larger than Europe. The gain they acquired via the technological innovation linked to defending themselves from the cold. The second example of this kind of application regards the evolution of our brain anatomy, and again of my throat. Okay, I'll try to keep it simple, of course, because I don't know how many people in the audience know about Brodmann areas and the functioning of particular areas of the brain. Do you? Okay. Okay. I don't either, so I can tell whatever I want. Anyway, in modern times, it is possible to produce a replica of the brain, even without a brain. What it takes is having CT scans of fossil skulls, easy, no? And once you have these CT scans, you can apply some special algorithms that do produce the brain. I'm going to show you in a moment how. We produce one of those algorithms, so whose name is Endomaker. It's freely available. In practice, you can imagine of a CT scan as a digital model. If you have a picture, you can define the picture in terms of pixels, right? With a digital model, which is three-dimensional, rather than the pixel, you have a voxel, which is the 3D version of pixels, that's all. In the case of a skull, all the bone areas are occupied by a special type of voxels. Of course, the internal cavity, which is somewhere here, where the brain belongs, it is without any voxel occupied, of course. So the algorithm just finds for that cavity, and once it has found it, it projects on the outside until the voxels of the bones are met, so that the end product is a brain. Exactly like that, and it's very, very fast. So you can do that very easily, provided that you have the CT scans of the scalp, which is the hard part, as you can imagine. The first application of this software and related algorithm was to study the evolution of brain asymmetry. The human brain is highly asymmetric. If you imagine, do you know how our brain is done, right? We have two hemispheres, but the two hemispheres are not the specular image of one another. In fact, it's like the left hemisphere is rotated and overgrown over the right hemisphere. It's terrible to see. It's like that. This is the brain from the down view, okay? From the throat. And you can see how strange it is, because one of the frontal goes above and beyond the other frontal, and the opposite happens to the occipital lobe down there. It is important to study asymmetry because our brain, differently from the brain of most other mammals, do some function on one side only. One of those functions, the best known example of this lateralization, as it goes by name, is speech. You produce speech just with the left side of the brain. The right side do not participate in speech production. And other very well known difference is that the arts are on your right side, the maths on your left side. So if you are not good at maths, you know which part of your brain you have to blame for that. So we studied asymmetry also because the medical literature is replete with examples of people with non-asymmetric brain who have some limitations in producing higher cognitive functions. They have speech impairment, they have difficulties in focusing and stuff. So it has to be important somehow. We studied the lateralization, calculating an index of asymmetry upon the brain. We go through the various steps of the analysis, and what we found that there are 3 species of Homo which again went through a real jump in evolutionary terms in the degree of asymmetry, and these 3 species of Homo are again Homo heidelbergensis, Homo sapiens, and Homo neanderthalensis. You can find them up here. So it's a same triplet that we found for the evolution of climatic natures. But we wanted to do more, just because we know a lot about brain functioning in modern humans. If we could, in a way, pinpoint the specific areas of the brain which are under selection, which went under selection during our evolution, we could understand which special aspects of our cognitive functions were preferred by natural selection. Of course, our hopes were to find that Broca's area and Wernicke's area, which are areas of the brain, do like I do. Do the same as I do. Do that. Don't be shy. Here is a Wernicke area. When you think to produce some sounds who make sense, this area is activated. When you eventually produce the sound, this other area on the left temple, which goes by the name of Broca's area, do produce the sound. If you take a very hard fist in this area of the brain, you cannot speak. It's called Broca's aphasia. Just depends on the fact that that special area of the brain has been deactivated for a little while. So our hope was to find that. And what we did, we developed a new algorithm that could translate the rate, could actually map the rate on the phenotype, the evolutionary rate. That way we could understand where selection was acting in particular. This is a very simple example. There's all familiar stuff. It's known that our brow ridge are much less developed than in Neanderthals, and you can find evidence of this here. Red means reduction in evolutionary terms, blue means expansion. So it's obvious that Neanderthals has much more pronounced brow ridge as compared to modern humans, right? Same if you compare the skull of a modern human to the skull of Homo erectus, you find, again, the brow ridge and stuff. So this is all familiar, just to let you understand how the software works. It is important, by the way, to understand where the rates are more important, because rates are tantamount for natural selection. If an area, a phenotype, a part of a phenotype is under selection, the rate of evolution will be high. Or the converse under stabilizing selection. And then we use the same software to study the evolution of the brain. The problem with the brain is that in terms of resolution, we have to understand where the brain, how the brain maps through, how the rate maps through the brain in very fine detail. We eventually find a solution to do that. So this is the endocast as it is produced, but the brain is like that. So we had to find a way to translate the brain on the endocast, which is our starting phenotype, directly on the brain. We eventually found this solution. You have to believe me, it's like that. And applied a technique which is known as geometric morphometrics, which is a geometric rendering of the shape as a whole. Then we use the geometric morphometrics to study the evolution of the brain in Homo. And this is what we found. Jumping. If you look at the whole primate clade, the area under selection is the yellow one. It's the prefrontal cortex. It's a well-known fact that primates have very large prefrontal. So far, so good. Nothing special, it's something that is known. But if you go to the anthropoid primates, you see something different, because besides the frontal cortex, there are other two areas which are involved, which are interested by high rates of evolution in terms of cortical expansion. And this area are the posterior parietal cortex over here and the inferior frontal gyrus. Now again, don't be shy, follow me. If you put your hand on top of your skull, not just on top, but immediately below the top, here, you see a flat area. That flat area is exactly above the posterior parietal cortex. The inferior frontal gyrus is here again on the temple on both sides, both on the left and on the right. Moving to hominins, the picture does not change. It's again the posterior parietal, the prefrontal, the frontal gyrus. But when you go to Homo sapiens in particular, something strange happens, because there are two other areas which are involved. This area in particular here is quite special. It goes by the name of angular gyrus. The angular gyrus on the left is the house of Wernicke's area. And we found the angular gyrus being interested by very high rate of evolution on both sides. Of course, we are not happy with a resolution like that, so we revert to the original landmarks. Landmarks are those points which are the unit of sampling in geometric morphometric terms. And we started to select the landmarks interested by the highest rate, just starting from the evolutionary model. And again, you find here is the posterior parietal, again in the anthropoids. This is the frontal cortex, and the frontal and prefrontal cortex in humans. And in Homo sapiens, we found that these areas are special because there is a brain network in our brain functioning that goes by the name of default mode network that does something special. Even the story of how the DMN was found is special. I have 2 minutes to tell that. Hey, put your mobile down. I had them? 5 minutes, okay, it's enough. Back in the day, some 20, 25 years ago, they were doing experiments to understand which area of the brain are activated when people do a special task. In this kind of studies, people are volunteering to be subject to the experiment, of course. And between experimental sessions, they noted that people, they didn't remove all of the machinery from the head of the people each and every time, of course. So between one session and the next, all the machinery was there. And they noted that during the breaks between the sessions, all of the participants had those areas activated. It was strange because it wasn't completely unexpected, and those areas are what now it's known to be the default mode network, which are the prefrontal cortex, especially along the midline, the posterior parietal cortex, the angular gyrus, and the temporal cortex, which are exactly the same areas that are interested by a high rate of evolution in Homo sapiens. But the other nice thing is what the DMN actually does. What is this network good for? This is just to show you the location. How many minutes I have? Now that you have to look at your mobile, you're not looking at it. How many minutes to show? I'm kidding, you know me. How many minutes do I have? Okay. Since then, it has been studied a lot because we now know very, very, very fairly well that the default mode network produces most of what we understand as especially humans. It produces mental time traveling, for example. Have you ever experienced the idea of projecting you in the future or in the past? The answer is yes. Come on, help me. Have you ever imagined yourself in side situation that you never lived? Have you ever imagined how people would react if you say to these people you are interested into sentence A rather than sentence B? Yes. Yeah, of course, we all do. We all do. We do that all the time. We are the only ape which is able to lie. To lie, it takes exactly that. You have to imagine the mental state of another person to anticipate this reaction. This special faculty of humans goes by the name of theory of mind. Do you know who the best producer of the theory of mind? The default mode, of course. And by the study of Shearer up there, we know that most of the language is produced by the default mode network. Which all boils down to the idea that the evolution of the human brain was really driven by selection for the production of high-order cognitive functions. This is exactly what we are special. And if there is a single phenotype that you should look upon to understand all of that, I find a sentence in a paper of Ian Tattersall that I have been lucky enough to review last year, which is this very sentence. We modern humans reconstruct our surroundings and experiences into a vocabulary discrete man. Okay, you can read, I know. This is what is being human. We talk to our own heads. We live in a parallel world which is not the world that all of the other species experience. We do experience a real world, of course. But most of the time we live in a world of our own, which is that, just in our brain. And the producer of that world is the default mode network. That's it. Thank you.